over the other. We're leaving philosophy now and moving into something that will soon become algebra. The measurement model. This is the machine by which yardsticks are made. It constructs and maintains. They're both important. If this yardstick was made of butter, it would be hard to maintain, and it would soon be useless. Or if it was a tape measure, it might become useless after a while because being stretched and so on. So it's very important that the machine not only constructs but maintains it in the, I can't measure red hot coals with this because it tends to burn it up, you see, so you have to also have a sphere of application in which the maintenance is undertaken. So this doesn't mean forever and everywhere, but there is a sphere in which the device has to work. And you need to maintain it, keep track of how it's working. If I was using this and using this and using this, I might want to notice that I was wearing away the bottom, and that after a while people were getting a little bit taller than they should because this started at 1/2 inch off the ground now instead of 0, according to this device. Okay, stochastic. Now here's a fancy word which you ought to put in your mind and gradually develop insight into. It constructs and maintains. Stochastic means probabilistic, not perfect, not deterministic, but probabilistic. Stochastic, conjoint. It means it links two different things together, like the object and the agent, the item and the person, the item and the student. There are always two things, and they have to have a conjoint relationship. And what kind of relationship must that be? Additive. It's not additive. Now, that's the same as multiplicative. You could put multiplicativity here if you wished. There's no difference in practice between additivity and multiplicativity, because if you take the logs of a multiplication, you've got an addition. If you take the log of a division, you've got a subtraction. Everybody know about that? Be sure you know about that, because that's very important. All this idea that there are ratio measures and interval measures is based on claiming ignorance of logarithms. But that doesn't seem intelligent to me. And the reason we stress additivity instead of multiplicativity is because we visualize additively. We visualize according to what it takes to navigate safely. And our navigation is in the space in front of us, which is a plane, by and large. And we think the dimensions in this direction and that direction are the same. And by seeing that sameness, we manage to get around without getting hurt. And so our eyes, which are our most comprehensive analytic tool, are trained to look at XY plots, where the axes are controlled in both directions, preferably the same, or at least each interval axes. If this is height and this is weight, they're not the same axes, but they at least will be uniform, interval, linear this way and linear that way. So that the changes in position in the plane defined by weight and height will be interpretable to our eyes. We don't want to plot numbers that are ratio numbers because the scale is changing all the time, and so we will misread such plots. That means that things like income, which have a ratio interpretation, namely it's better to have twice as much money than to have $1 more, so that what's uniform in things like income is the ratio, not the difference. Then if you're going to plot income, you take its log, so you can see what's happening. Okay, that's what the additivity means. We must also have parameter separation. That is, the B and the D, the person and the item, the object and the agent, which meet, conjoin. Under a stochastic model, there has to be a P somewhere here, have to combine in a linear way, as a difference in this case. And when we go to estimate these two things, the formulation of this expression must enable us to find out where this is, regardless of which items we use. We need to know how much math Kathy knows, regardless of which questions we ask her, as long as they're math questions. Otherwise, all we know is what she knows about this test. And that's not worth anything as an inference. We want to infer what she's going to know about some other tests we haven't given her, which means we have to extract from her test performance something which applies to any test like this. It cannot be limited to the test she took. When you measure my height with this thing, it's got to apply to any yardstick that you might use. I mean, when I mail this to my tailor in Hong Kong, wish I had one, and he gives me a nice suit, we assume that my yardstick and his match well enough so that the suit will fit me. Otherwise, we couldn't do business. So there has to be a separation between measuring this, obtaining a measure for this, and obtaining a measure for this. That's why I say parameter separation. This next thing is, in fact, an unavoidable and useful concomitant of that. Because if you have this, you have this. So this is really a footnote to modern statistics. That is, we would like to have something that we can do with the x's, some combination of the x's, some way to put them together, which gives us a statistic. A statistic is always a function of the data, which is sufficient. That is, it contains all of the information that the situation is claimed to have with respect to the measure that that statistic is supposed to provide. So we're going to look for sufficient statistics, but further research into these things has shown that these are the same thing. In fact, all of this is one thing. These are just different names for one configuration. All right, here's the picture. We want a line, a ruler. Notice that all measurements you know about, whether they're heat or time, are always laid out on a line. Sometimes a line is a circle, like a clock face. But we express every measurement as though it were a yardstick, because that's the original distance. So all measures are distances. And so when we draw this line, that's not just a happy guess. I'm going back to the roots of the idea of measurement by drawing this line. And I want you to always be thinking about the yardstick. All right, here's Mike right here. Here is some question we might ask him. And what is the relationship on the line between Mike and the question? Well, there's only one relationship that comes out there. It's the distance between them. That is it. That's all we know about this. That's all we want to know. So it's B minus D that we're interested in, not B times D, and in this case, not B plus D, although we could. This is difficult. We could call it easiness and change its sign, but we're just confusing ourselves. This is the natural way to look at it, the distance between these two. So this distance, which contains the additivity, and which contains the conjointness, the conjoin of a person and an item, has to produce a P in some way or other. Okay, we want this. What do we have? We have Mike taking the question and either getting what we call a right answer or not. And what we want to get over here to a probability which will tell us Mike's measure and will, if we want, tell us the calibration of the question we asked him, and which will be the idea or the abstract representation of this concrete experience. It will be what this means to us. And the meaning will go through P and come out to a measure for Mike and a calibration for the item. And we need X is seen in terms of P. P has to be a function of B minus D, which separates B and D. That's what I'm saying down here. So here we have the data, we have its meaning, it has to be a distance, has to produce separable measures. So this is want, have, use. Now we're going to go a little further. We've got to get P of X equal to a function of B minus D. Well, we can draw a picture of what it has to look like. P of X goes from 0 to 1, and B minus D goes from minus infinity, that's a little bit over here, to plus infinity, that's a slight way up over here. And as it goes through 0 here, that's when B would equal D, because B minus D would be 0. So we've got a very long line here. In fact, nobody's actually figured out how long that is. And we've got a rather short line here, just 0 to 1. And we can see that as this gets bigger, that gets bigger. So we can draw in what this is going to have to look like. It's going to have to be this ogive, like this. And we see right away it's curved. It's not straight. That's an interesting thing, which we'll come back to. All right, how are we going to get from here to here? Well, let's start. We know that the probability, Px, according to our choice of the situation, goes from never to always, or will never happen is sure to happen, 0 to 1. If we take this and divide it by the other probability so as to make odds, we know that will go from 0 to infinity. Why? Because as this goes to 1, this goes to 0. As we divide by 0, you see, this gets smaller and smaller and smaller as this gets closer and closer to 1. So this will go all the way to plus infinity. So we've solved part of the problem right there. Now, if we take the log of this thing, when it's 1, the log is 0. As this thing goes to 0, the log goes to minus infinity. And on the other way around, the log of infinity is infinity. So we've now got it between minus infinity and plus infinity. And why not let that be the model? What could be simpler? So we'll just say this will be defined as equal to that. Here it is, log of p for a right answer over p for a wrong answer. Or we could say the log of p when x equals 1 over p when x equals 0 will be defined as the difference between the measure of person n and the difficulty of item I. Now we can solve this equation for p and I, and it'll come out like this. That is, p and I equals the exponential function of b minus d over 1 plus. That's awkward. This is really easy to see. Log odds defined as the difference. We got everything there. We got the additivity. We got the conjointness. We will soon see we've got the separation. And we got it in the simplest possible way. There is no simpler way to get this to transform to that. As a matter of fact, though, we could use much more complicated methods for doing this. We could say we require separability of parameters. What model must follow? Or we could say we require sufficiency in the statistics. What model must follow? Or we could say we require conjoint additivity. What model must follow? And in all cases, the answer is the same as this. So while we could get here by very sophisticated methods with a certain amount of algebraic deduction, we could also get here by just kind of commonsensical reasoning. Say, well, if we have to get a function for here, and we know what the limits of this is, and we know what the limits of this is, what's the quickest way, simplest way we could get from here down to here? And here we go, 1, 2, and we've done it. First we take the odds, then we take the log odds, and we got it. And this is not only the simplest answer, it's the only answer. There is no other function that's going to meet the requirements, that can meet the requirements of conjoint additivity, parameter separation, or sufficient statistics. So it's not like this is just a lucky choice. It is unique. Now, there are a lot of people in social science still struggling to have more complicated answers to this problem. And they just can't believe that it would be all right to have such a simple one. So they make it more complicated. We won't spend time today on them. You may meet them occasionally. If you do, say, let's take some data and try your method and see what happens. Because if you do, and if you cut your data in half, say the more able people and the less able people, and try their method, you will find you get different answers, showing that their method is not independent, that their parameters are not separable. You'll also find that you don't have sufficient statistics for their parameters. So if you actually apply these more complicated methods, you discover that they, in fact, don't help you solve the problem. Properties of the model. We have found a function now for p, which is the meaning of x, in terms of b and d, which are separate measures on the same variable. This is their difference, additivity. We see additivity right in there. What about conjoint additivity? Well, if we take the lowest person and order the persons from the lowest to the highest, and we take the hardest item and order them from the hardest item to the easiest item, we will find that the probability is lowest here, and that it goes up continually along this line and in every column, and that it goes up continually in every row until it comes out here at the top. And that's a Gutman scale, if you know what a Gutman scale is. Perfect ordering, perfect conjoint ordering in the probabilities, not the data. The data suffers from the vicissitudes of being real, but the idea, which is the probabilities, is perfectly ordered. So we have this conjoint additivity. And if you take b minus d and do it through here, just whatever b is, this is the lowest, this is the highest. Whatever d is, this is the highest, this is the lowest. And you fill in all the b minus d's, you will find that they increase. Every column increases down, every row increases to the right. And since P is a monotonic function of B minus D, it has the same properties. So you have conjoint additivity. Parameter separation. Just call B minus D GNI. And now compare GNI with GMI. Say two different people, but the same item. Well, the item cancels, and you have the difference of the people without an item there. So this means you can compare people regardless of which item you give them. And you can do the same thing for items, and you can compare items regardless of who you try them out on. So with this very simple little grade school algebra, you can show that you have parameter separation. That is, you can separate my height from the yardstick, and you can make the yardstick without knowing you're going to use it on me. And finally, sufficient statistics. This is a little denser here, but in finding a good value for B, we use an iteration process. Here is a good guess. Here are the x's that we've collected. Here are their expectations based on this guess of B. And here is P1 minus P. We'll come back to that in a moment. And as we add this up, we find that we're adding up the x's. That is, we are producing the raw score. So as we look at this equation by which we improve the estimates of B, this is also the estimation equation for B, we see that the statistic, that is the function of x's, which operates in here, is just the sum of them, or just the good old famous raw score that everybody has always been using. So there is a very firm connection with traditional practice. Traditional practice has been doing all their statistics on the raw scores, but the raw scores have the problem of the oranges. They're counting big and little oranges and sometimes tomatoes and all kinds of things like that. So that count is out of control. It also has the problem of being like the probability. That is, this is a picture of a test. This is 0%. This is 100%. And these are the items on the test going up here equally. 1 right, 2 right, 3 right, 4 right, up to 100 right, say. But notice that the meaning of those items is changing, because a couple of right answers here are not as worth as much as one right answer out here because of the way this curve is changing. The exchange between right answers and amount of distance between B and D is gradually shifting. So if, in fact, you're up here, say, if it's a 100-item test and you're up here at about 98 items, one more right answer here is worth 3 or 4 down here. Now, you might say, well, how do you know that? It's very easy to do an experiment which doesn't involve any of this to prove that to yourself. You have two groups of people. Some of them are getting 98, 97 on the test. Some are getting 50, 51, 52. Okay, you take the people who are getting the high score, you give them a harder test. You give them a test of the same kind, hard enough so they're now at 50. And you'll discover that the average difference, that all the people who were at 97 and then 98 on the easy test, when you get them down on a harder test where they're at 50 or so, you'll find that the 97s were averaging around 48 and the 98s are averaging around 52. So you can observe the nonlinearity of the raw scores produced by the boundary of them from 0 to 100% without knowing anything of the things I've been saying at all. A very simple experiment. Just shift the test and see what happens to the same people. You could even simulate that with a long test with lots of hard and easy items by taking the easy part of the test. You could take a group of people, you see how they do on the easy part of the test. Maybe you divide them up into steps on the easy part of the test. If it's 50-50, suppose you take the 50 easy items. So you say, well, let's identify the people who got 49, 47, 48, 47. Now, let's look at how they did on the hard part of the test, where they're not getting 47, 48, 49, but maybe they're getting 25, 26, 27, and that kind of thing. And you'll find they're further apart on the hard part of the test than they were on the easy part. Well, you can see right away that that means that counting raw scores is like counting oranges of different sizes. And there's no need for that, since you can use this transformation to straighten it out. Now we come to the benefit of the model being very demanding. This model is real simple. It says nothing is supposed to happen here except what B does and what D does. So it's taking a very idealistic, very demanding approach to a messy reality. So you might say, well, fine, but who will believe this? How do I dare go go aloft in this airplane that's got a good theory behind it, but what if it crashes? What if the wings don't work? How will I find out how things are going? Well, when you start downtown in your car and you're out on the outer drive, how do you find out if things are working all right? You pay attention to what's happening from moment to moment. You see if you're in the right lane, and if you're not quite in the right lane, correctly in the lane, you move over a little bit this way or that way. So, same thing with this. You collect a bunch of X's. Objects N, agents I produce some observed responses. And you construct some P's to match them as closely as possible. And you choose your B's and D's through that very idealistic and demanding function for the P to bring the P's as close to the X's as possible. And then you have, in this binomial case where X just has two values, you have what you expect X to be, which is P and I, and what you think its variation around its expectation should be, which is P and I, 1 minus P and I. Now, you look at that. That's the score residual. And if you want to standardize it, you can divide the score residual by its standard deviation, the square root of its variance. So you have a standardized residual. If you have a whole matrix of these things, every time a person takes an item, you have a standardized residual for how it was for them with that item. Now, if P is doing a good job explaining X, then these should all be reasonable, like they should be near 0, or maybe between -2 and +2, or something like that. They shouldn't be too wide, between -3 and +3. If, on the other hand, there is a moment in here when this person did something very surprising with that item. It was much too hard for them, but they got it right. Or it was much too easy for them, but they got it wrong. That's going to stick out. They're going to have a big Z. So you're not flying blind here. As long as you look at the matrix of residuals in various ways that have to be made convenient to the eye, you will see if anything's wrong, and you will learn what to do you will learn from the measurement analysis of your data how to improve the observation model so that it produces measures worth analyzing. You don't want to start this until you got this worked out. So as you see misfits, residuals that are too big, you go back to the observation model and you look at the item. If it's an item that seems to be doing it, you say, oh, no wonder, this is an ambiguous item, or this item is miskeyed, or this item is on the wrong topic, or whatever. And you often find that. Or if you find that a lot of these are surprisingly big standardized residuals are piling up on a person, you say, what's this person doing? And maybe you find out they just filled out the fifth choice on every item if it was a scan sheet. Or perhaps they were sick, or perhaps they got their answer sheet upside down, or something like that. But you look for events in the material which are not the ones you want there, and then you do something about it. Now, here's a little rule of thumb that you can use for this, if you're willing to look at each response. The expected value of a standardized residual is 0, because if X is the same as P, that means we've made that P has explained X as good as possible. The variance of a standardized residual is 1. So the probability of any particular X is 1 over 1 plus Z squared. It's less than that. So that's fine, because here we have a column of Z's, and here we have a column of PX's calculated according to this formula. And we see that when Z is 1 or 2, the probability of it occurring is 1/2 or 1/5. That's not so improbable. But when Z is 5, the probability of occurring is 1/26. It's becoming unlikely. It's becoming unacceptable. It's becoming, we've got to do something. 3 is the turning point. Below here, it's not improbable enough to really take exception to. But above 3, in the 4 and 5 range, you're now getting down to probabilities so low that it seems worthwhile to investigate, to diagnose, and perhaps to reject. Now, this rejection, that's not throwing away data. If your first step here is to define a variable, you're interested in the D's and the item difficulties. If some people are behaving goofy, you don't want them in there. So when you observe a person producing standardized residuals up around 4 or 5 or bigger, better to make those responses from that person blank temporarily than to keep them in there. When you get back to doing a job for that person, you can put their responses back in and figure out what to say about them. But at the point where you're constructing the yardstick, those anomalies will not help construct the yardstick. Take them out of the data. Maybe you want to take the whole person out. If the person's behavior is so erratic that you're suspicious that you can't believe anything that they're doing, then take them out temporarily. But if it's just a couple of things they did, maybe it was a random error at that point, maybe they misread or something, so you can just take out that response and keep the rest of that person's behavior in. So there is an invitation when you're constructing the ruler to review the z's, the standardized residuals, and to make missing temporarily the responses which are contradicting your intentions. But always look and see where it's coming from, because what if this person doesn't belong in the sample? Or what if this item doesn't belong in the test? And then you wouldn't just make the response missing, you would remove the uninvited person or the unintended item and continue your construction. Now, of course, if you have 100 items and 1,000 people, now there are then 100,000 of these things to look at. So we need devices for expediting that, and that's one of the things that Mike and I and others worked on, and Kathy, how to make the residuals easier to analyze, so you don't lose the information in them, but you don't spend hours and hours looking through tables of numbers, because that's very, you need pictures of this, really, if you can get them, and we have to invent good ways to picture this kind of problem in order to pursue the best definition of a ruler.